Under the subject of geology, we study the earth. The term earth science is a further enlargement of the perspectives covered under geology and is defined as the science dealing with all aspects of earth in which we live. A thorough understanding of the earth's processes and their ramifications have great relevance to the societal development and the progress of the nation. In UGC model curriculum, structural geology is prescribed as one of the fundamental paper of earth science. Structural geology is a subfield within geology which focuses on the study of geological structures with the goal of learning how, when, and why they form. A structural geologist identifies geological phenomena looking specifically for signs of deformation which show the kinds of stress put on the rock as it forms. Deformation can reveal the angles of stress, the origins of the stress, and its intensity. How things form and change over time, a specialist in structural geology can draw a number of conclusions which may be used to gain a deeper understanding of geology. Primary data sets for structural geology are collected in the field. Structural geologists measure a variety of planar features, that is, bedding planes, foliation planes, fold axial planes, fault planes, and joints. Both petroleum geology and mining geology, folded and faulted rock strata commonly form traps for the accumulation and concentration of fluids such as petroleum and natural gas. First paper of UGC model curriculum has covered the introductory part of structural geology, and sixth paper of the curriculum is fully based on the topics of structural geology. Sixth paper of structural geology includes following topics: fold morphology, geometric and genetic classification of fold, mechanics and causes of folding.
Dear friends, we have discussed in detail about the geometrical properties of folds, their morphology, the classifications of the conventional kind and the classification on quantitative basis as proposed by Professor Ramsey. Now that we know all about the geometry of folds, it is our turn to learn about the processes, how the different types of folds are produced in nature. Before we go into the different mechanisms of fold formation, one thing we must be very clear at the outset. It is this, that the layers in a rock which is normally a brittle substance which cannot really bend, how can these layers show continuous regular curvature? To understand this, we need to go into the behavior of materials under enhanced confining pressure and temperature condition. We must understand that most of the deformation of rocks takes place at a depth below the earth's surface. The tectonic processes that move the lithospheric plates around on the earth's surface cause deep seated deformation in the rock layers. If we draw a comparison, you can see that bar of iron, which is normally very brittle, very hard and cannot be routinely bent, gets easily molded into any shape we want when it is subjected to heat. A red hot iron bar may be molded into any shape we want. Similarly, glass, which is a very brittle substance, breaks at the strike of a hammer, can be shaped into various forms when it is hot. The continuous curvatures or folds that develop in rocks are produced following a similar mechanism. The layer of rocks below the earth's surface, where the depth causes an increase in confining pressure and temperature, makes the otherwise brittle rocks much more malleable, so that it can withstand a directed stress to a greater length without breaking, and during the process may show ductile deformation resulting in folds. The shape of the folds is naturally dependent on the force or mechanism by which the regular curvatures are being formed in the rocks. There are two basic mechanisms of fold formation in nature, while a third or less important mechanism is also responsible for some of the folds. The early 20th century, structural geologists have been trying to understand the mechanism of fold formation in nature by making mathematical modeling and experimental work in the laboratory, trying to simulate fold formation by assuming the physical property of different materials. All the scientists working on the mechanism of fold formation, Bio and Ramberg, two leading scientists, have been able to analyze the mechanism of fold formation very successfully. Bio and Ramberg's models say that the rocks behave like viscous material, a Newtonian fluid with a very high viscosity coefficient when subjected to high temperature and high confining pressure. One mechanism of fold formation is where the directed stress responsible for fold formation is applied parallel to the bounding surfaces of a layer. Bio and Ramberg arrived at a conclusion that when there are layers of different viscosity coefficient within a sequence of rocks, and especially a layer of higher viscosity coefficient mu 1 is embedded or sandwiched between two layers of lower viscosity coefficient mu 2, then a buckling instability is set up at the interface of the two layers. According to them, a number of wavelengths start forming when the buckling instability sets in, but of these one wavelength dominates the other while the others flatten out. The wavelength that dominates the fold formation as the layer parallel directed stress continues to fold the multilayered sequence is called the dominant wavelength. The fold formation by layer parallel directed stress is known as buckling or flexure. The dominant wavelength or WD is represented by the equation twice pi t cube root of mu 1 by 6 mu 2, where T is the thickness of the layer that is being folded and mu 1 and mu 2 are the viscosity coefficients of the two layers. Mu 1 is greater, mu 2 is lower. It has been observed that if instead of a single layer, the layer mu 1 consists of n number of layers with perfect lubrication between each of the thinner layers, the dominant wavelength will be represented by twice pi t cube root of n mu 1 by 6 mu 2. It has been observed that when a single layer is deformed by flexure or buckling, like the thick rubber sheet, what happens is that there is an extension of the upper boundary and a shortening of the lower bound. When the fold formation affects a multi-layered sequence, this differential deformation of the upper and lower boundaries of each layer results in a layer parallel slip. Thus, the mechanism of fold formation responsible for folding a multi-layered sequence by application of directed stress parallel to the layering is known as flexure slip. Because of the peculiar response of the layers to the applied layer parallel directed stress, the geometries of the folds are affected. Because of the layer parallel slip, there is a sense of displacement between the layers parallel to the layers, as a result of which minor folds form on the limbs, and the minor folds on the limbs are asymmetrical in nature, being dextral on the left limb of an antiform and sinistral on the right limb of an antiform. The formula for dominant wavelength also directs that layers with smaller thickness will develop smaller wavelength folds and layers with thicker boundaries will develop larger wavelengths. Thus, folds formed by buckling or flexure slip will be disharmonic in nature, layers of different thicknesses showing different wavelengths of folds. Within a single layer deformed by buckling, the differential strain extension along the outer boundary and shortening along the inner boundary results in the development of a neutral surface somewhere within the layer, whose length remains the same before and after deformation. Because the neutral surface separates a folded layer, a buckle folded layer, into a zone of extension and a zone of compression or shortening, different features develop along them. Above the neutral surface, we find that extensional structures such as extensional joints or normal faults develop, while within the zone of shortening in the inner side of the layer, compressional structures like minor folds and thrust faults develop. If in an experiment original circular markers are put on the layer to be folded, these circular markers will be deformed into ellipses, and the long axis of the ellipses after deformation will be systematically disposed against the axial plane of the fold. This results in actual rocks also. The cleavage plane, as we will be discussing later, develop parallel to the planes of flattening, that is perpendicular to the direction of shortening, and they show a radial distribution against the axial plane, resulting in the convergence of cleavage or convergent fanning of cleavage. So, these are characteristics of buckle or flexure slip folds that are produced by a layer parallel directed stress. The features developed in rocks in the field helps us in understanding the fold mechanism with the help of these features. In the second type of fold mechanism, which is called shear folding or passive shear folding, the physical property of the layers have nothing to do with the fold form or wavelength, amplitude, etc. Passive folding or shear folding results when a set of close spaced shear fractures like faults develop across a marker horizon. If there is displacement along these shear planes, small scale displacements that result in the deformation of the rock layer, the original planar marker horizon may get folded. For folding to develop through this process on a marker horizon, three things are necessary, three conditions must be satisfied. Number one, the shear planes that develop across the marker horizon must have the slip direction at an angle to the line of intersection between the marker horizon and the shear plane. If the slip direction is parallel to it, then no fold will be produced. The second condition is that the sense of shear, the sense of slip along these shear planes must be reversed at regular intervals, marking the fold hinges. If they are not reversed, then the orientation of the plane will change and not get folded, it will still remain a plane. And the first condition obviously is that the shear fractures must develop at an angle, at a high angle to the marker horizon. If they are developed parallel to it, then no folds will be produced. If we now compare the morphology of the folds produced by shear folding with those produced by buckle folding, we will see that here whatever be the layer thickness, all layers will undergo the same amount of displacement in the same sense. Thus, the curvature that is produced on the different layers irrespective of their thickness will be identical, while in case of buckle folds or flexure slip folds, the outer and inner boundary of a layer are mutually parallel, producing concentric or parallel geometry, or more specifically class 1b folds. Folds that form by passive shear folding will have identical curvature of all the layers, resulting in the development of similar folds or folds of class 2. The flexure folds and shear folds can also be identified in the field by the development of different structures on the outer arc and the inner arc of the folded layer. As we have discussed, we find extensional features on the outer side of a flexure folded layer, and the inner side of the layer shows compressional features. But in passive shear folding, there will be no such differences on the outer and inner arcs of the folded layer. In addition, while the foliations that develop in response to the applied layer parallel stress in case of flexure folding show radiating cleavage planes or convergent fanning, in case of passive shear folding, the cleavage planes will develop parallel to the planes of shear, the shear fractures, and will be essentially mutually parallel and parallel to the axial plane of the fold. Thus, the morphology of the fold as observed in the field or in the hand specimen can easily lead a structural geologist to identify the mechanism of fold formation. The third less important mechanism of fold formation, known as bending, takes place when a layer of sediments lie over uneven, hard, compact basement. The load of the overlying sediments pushes down on the layer, and the irregular, hard, compact basement puts a vertical pressure on the horizontal sedimentary layers, thus compressing them and forming folds in them. Where there is a basement high, the sedimentary layers are compressed more, resulting in the development of an antiformal hinge where the orthogonal thickness is minimum, and where there is a basement low, the sedimentary layers get less compressed, resulting in the development of a synformal hinge with maximum thickness at the synformal hinge. Thus, if we try to compare the fold geometries produced by buckle or flexure slip, passive shear and bending, we will see that the buckle folds or flexure slip folds correspond to class 1B folds of Ramsey or concentric or parallel folds. The folds formed by passive shear, they correspond to class 2 of Ramsey or similar folds, while folds formed by bending by vertical pressure acting perpendicular to the layering, they result in the supratenuous geometry, minimum orthogonal thickness at the antiformal hinge and maximum orthogonal thickness at the synformal hinge. Now that we have gone through the mechanism of different types of fold formation, let us discuss the method of understanding the mechanism of folds from field. It is folds with linear hinge lines or cylindrical folds. When we measure the orientation across a folded surface and plot them in the stereographic projection, they generally plot along a great circle, and the pole to this great circle defines the fold axis. This discussion will be clearer when we discuss the principles of stereographic projection and use of stereographic projection in structural geology. Now that we have reached the end of the episodes on folds, let us summarize what we have learned. The first two episodes deals with the morphology of folds, the understanding of the different parts of a fold, the naming of various types of folds depending on the shape of the fold on the profile section, the orientation of the different parts of the fold. The second episode goes into the classification of folds using more quantitative means proposed by Ramsey, and in the third episode we have discussed in brief the two major mechanisms of deformation as established by different workers and a third less important mechanism. In case of fold mechanism, the first mechanism by flexure slip or buckle considers or simulates the rock layers into materials of Newtonian properties, ideal viscous substances with high viscosity coefficients, and in case of buckling, the physical property of the different layers, they are very important in defining the morphology of the folds. We have finished discussing features produced by ductile deformation in a rock by application of directed stress.